Hello and welcome to Engineers Mindset Academy. So in today's class, we are going to begin a different topic which we have seen over time being repeated in the Jamb examination physics questions. So the topic we are going to be dealing with today is thermal expansivity. And as you all know, at the end of every topic discussed, we are going to be wrapping up with about 2 to 3 years past question review in Jamb physics examination questions. So sit tight while we begin the class. Welcome back. Now, before going into thermal expansivity, let us understand what is heat. Heat is a form of energy which is called thermal energy. Now, we all know that if we place a kettle of cold water on a heating device, let's say like an electric cooker or a gas cooker or even your stove, after a time, what happens is that heat is being transferred from the stove or the heating device into this cold water in the kettle. And notice that the temperature between the water now changes. Now, this goes on to tell us that heat is as a result of temperature difference between two bodies. Now, the direction of heat transfer can only be from a hotter body to a colder body. So you should also pay attention to this particular question. It might also come out in your Jamb examination. The direction of heat transfer can never be from a cold body to a hot body, but it can always be from a hotter body to a colder body. Now, temperature applied or heat applied on a body can cause lots of effect on the body. It can cause the change of state of that body. For instance, it can change a body from solid to liquid. Talking about ice, if you actually apply heat to ice, what happens is that the more the temperature is increasing, the more the ice is melting and completely turns into what liquid. That is changing from solid state to a liquid state. It can also cause a liquid to change from liquid state to a gaseous or a vapor state. By consistent application of heat to a liquid, after a while, what happens is that it starts transforming into what vapor, and eventually it becomes superheated and becomes what completely a gas. Okay, so heat can actually cause a change of state in the structure of a body. Heat can also cause change in temperature of a body. We've already explained that a body which is cold, when brought to a colder body, for instance, the idea I gave with a cold water in a kettle, and of course being in contact with a stove or a heating device, what happens is after a while, heat is being transferred from the heating device towards the cold water inside the kettle. So heat can also cause a change in temperature. Also, heat can cause expansion in a body, and that brings us to the idea thermal expansivity. Heat can cause expansion in a body. By expansion in body, it simply means the dimension of a body. Heat can cause the expansion in the dimension of the body. By dimension, I mean either the length, the height, or the width of the body. In general, heat can cause expansion in the shape of a body. So that brings us to the idea of thermal expansivity. Now, what is thermal expansivity? Thermal expansivity is simply the change in the dimensions of a body when heat is applied to that body. Change in the dimension of a body when heat is applied to that body. Now, there are three noticeable kinds of thermal expansivity. The first is what is called the linear expansion or linear expansivity. The next is called the area or superficial expansivity. And the final one is called the volume or cubic expansivity. So we're going to be talking in details about these three. What is linear expansivity? Linear expansivity is the increase in length with respect to the original length of the body per unit degree rise in temperature. Mathematically, linear expansivity, it can be denoted by the Greek symbol alpha. Okay, linear expansivity is denoted by the Greek symbol alpha. It is simply given as the increase in length with respect to the original length, multiplying by the temperature rise or temperature change. Multiplied by the temperature change. So this simply implies that alpha is equal to the increase in length is simply given as L2 minus L1 all over original length, which is L1 times change in temperature theta. All right, so where L2 tells us the final length of the given object, L1 tells us the initial length of this object. Same thing as here. This is also L1, the initial length or the original length of the object. And change in theta tells us what? The change in temperature. And this change in temperature, delta theta, mind you, delta simply means change. Now, this means what? Theta 2 minus theta 1, change in temperature, where theta 2 is the final temperature and theta 1 is the initial temperature. So, mathematically, the linear expansivity of an object is given as the increase in length with respect to the original length per degree rise in temperature. That is simply linear expansivity. The next type of expansivity we are going to be talking about is what is called the area expansivity or superficial expansivity. What is the area expansivity? Just like the linear expansivity states. Now, in the area expansivity, whenever a body increases in both length, height, and width when heat is applied to the object or the body, then we say the body has undergone area expansivity, or it has also undergone volume expansivity. When there is a change in not just the length of the body, but both the length, the height, and the width of the body when heat is applied, then we said there is an area expansivity or there's a volume expansivity. So the area expansivity, which can also be called superficial expansivity, is the change in the area of an object with respect to the original area and to the degree rise in temperature. It is simply the ratio of the change in area of the body with respect to the original area and the degree rise in temperature. Mathematically, area expansivity, okay, it is denoted by the Greek symbol beta, is simply equal to change in area or increase in area of a body with respect to the original area, multiplied by the temperature difference or temperature change. Okay, so you can simply say beta is equal to A2 minus A1 all over A1 multiplied by change in temperature, change in theta, where A2 is the final area of the body, A1 is the initial area of the body, A1 is also the initial area of the body, and of course, change in theta, as always here, means change in temperature, and it's simply given as theta 2 minus theta 1, where theta 2 remains the final temperature, theta 1 remains the initial temperature of the body. Okay, also the volume expansivity is the last one. Volume expansivity can also be called cubic expansivity. So it takes place along the volume of an object. That is simply saying the length, the width, and the height of the object. Now, if there's a change between the length and the width, or the width and the height, then you talk about the area expansion. But if there's a change along the three sides, the length, the width, and the height, due to temperature, then we'll talk about what? The volume expansivity. Now, volume expansivity can be defined as the change in volume with respect to the original volume per degree rise in temperature. So all the definitions are quite the same. The only difference is what? Their dimensions. If it is length, then it means change in length with respect to original length and what? Per degree rise in temperature. If it is area, then it means change in area with respect to original area per degree rise in temperature. And in the case of volume, it becomes change in volume per unit volume per degree rise in temperature. So mathematically, volume expansivity, it can be denoted with the Greek symbol gamma is equal to change in volume all over original volume, okay, multiplied by temperature change. Okay, multiplied by temperature change. So you're simply saying that gamma volume expansivity is equal to V2 minus V1 all over V1 times change in theta. We have V2 stands for the final volume, V1 stands for the initial volume, V1 as well, of course, is initial volume, and then change in theta means change in temperature. So these are all as a result of what? Thermal expansivity. I said earlier, thermal expansivity is simply the expansion which takes place due to what? Change in the dimension of, or due to the expansion in the dimension of a given object when heat is applied to it. So the three basic thermal expansivity which we encounter is what is called the linear expansivity, area expansivity, and the volume expansivity. I also mentioned a very key important factor that heat can only be transferred from a hotter body to a colder body. So if you're being asked what is the direction of heat transfer, what is the direction of heat transfer? It is simply from a hot body to a cold body. That's the direction of heat transfer. Also, it is important for you to know that the linear expansivity of an object tells us how far that object will expand in response to temperature. The linear expansivity of an object tells us how that object will expand in response to temperature. So different materials have different linear expansivity. This simply means that different materials has different rate at which they expand or respond to a particular temperature. For instance, copper expands faster than steel when they are both subjected to what? The same intensity of heat or temperature. Why? Simply because copper has a lower thermal expansivity or linear expansivity than steel. So the linear expansivity in copper is quite lower than that of steel. So that simply means that copper will respond to changes faster when heat is applied than steel. So that's another thing you should also what? Keep in mind in your examination question. These are alternate questions that could come out in your Jamb examination questions. All right, so having said all of this, let's pick an example to explain the concept of linear, thermal, and volume expansivity. Now, let's consider this question on the board. Question says, a copper rod of length 10 meters and temperature 20 degrees Celsius expands to a new length when the temperature is increased to 100 degrees Celsius. What is the new length? Take the linear expansivity of copper to be equal to 0.000017 per degree Celsius. Alright, so it is important for you to know that the linear expansivity of a material can be measured in per degree of Celsius or per degree of Kelvin. Alright, so let's pick out our parameters. So we are given that a copper rod of length. So a copper rod of length 10 meters and temperature 20 degrees Celsius simply means that the initial length or the original length is 10 meters and the original temperature is also what? 20 degrees Celsius. So original length, okay, you can call it L1. Most textbooks simply use LO for original, but you can call this L1, which means initial length is equal to 10 meters and original temperature as well. Original temperature was given, call that theta 1. Theta 1 was given as 20 degrees Celsius. Now, mind you, you are not to convert your temperatures to either Kelvin or Celsius. If it's in Celsius, solve with it in Celsius. If it is given to you in Kelvin, solve with it in Kelvin. Why? Simply because the thermal expansivity is measured, like I told you, is measured in per degree of Celsius or per degree of Kelvin. So it remains unchanged. Whether the temperature is in Kelvin or is in Celsius, just solve with it the way it is. All right, so we are given the original temperature to be theta 1, which is 20 degrees Celsius. And question said it is expanded to a new length when the temperature is increased to 100 degrees Celsius. So that means we have a final temperature now. Final temperature was given to us there, that is theta 2, and that's equal to 100 degrees Celsius. We are asked to find the final length, and the final length is unknown. The new length, L2, equal to, that's an unknown value. So we simply employ our equation for linear expansion, and we know that linear expansivity alpha is simply given as what? L2 minus L1 all over L1 times the change in temperature. All right, we are change in temperature, like I told you earlier, where delta temperature simply means what? Theta 2 minus theta 1, which means final temperature minus initial temperature. So let's obtain that as C. The final temperature 2 was given as what? 100 degrees Celsius. So you have 100 minus the initial temperature was given as 20 degrees Celsius. So 100 minus 20. So this will give us what? 80 degrees Celsius. So which means change in theta is actually what? 80 degrees Celsius. Alright, so let's represent the whole information here. We are asked to find L2, or we can simply make L2 subject of the formula first before solving. So if you're to make L2 subject, remember this alpha or this linear expansivity is same as saying alpha all over 1. It doesn't change. Okay, a number or a whole number or an alphabet on its own simply means that number or that alphabet divides by 1. So if you have 20, 20 is same as saying 20 all over 1. It still remains as 20. So alpha also means alpha over 1. Now this helps us to cross multiply. 1 multiplies everything at the numerator, while alpha multiplies everything at the denominator. So I'm going to have what? Alpha multiplying everything at the denominator, which is L1 times change in temperature. And this will be equal to, I will have 1 multiplying everything here. So 1 times anything remains that same thing. I have what? L2 minus L1. Now I am to look for what? L2. This is what I'm looking for, the final length. So which means I'm going to send what? Minus L1, which is the original length, back to this side of the equation. Now, negative sign, cross and equal to sign becomes what? A positive sign. Therefore, alpha times length 1 times change in theta is now okay. If I cross over minus L1, it becomes what? Plus L1, and this is equal to, now I am left with L2 on this side of the equation. So this is how to find your second length. Simply, L2 is equal to alpha L1 change in theta plus L1. Okay, so let's put in now our parameters and see. Let's put in now our parameters and see. So we've already made L2 subject. This now implies that alpha being the thermal expansivity. Let's do it over here. Alpha is the thermal expansivity, and it was given in the question as 0.00017. So take thermal linear expansivity of copper to be 0.000017. So we have, in place of alpha, it becomes 0.00017 multiplied by L1, which is the initial length, and the initial length was given as 10 meters. So multiply by 10, multiply by change in theta. Change in theta simply means change in temperature. We did that over here and we had 80 degrees. So multiply by 80. And this, okay, plus L1, which is the first length. Initial length is simply 10, and that's equal to what? L2. It can be as simple as this. So let's multiply everything here together. We have 0.000017, okay, 0.000017 multiplied by 10 multiplied by 80. So this multiple gives us 0.0136 plus the 10, and that's equal to L2. So this simply implies that the final length L2 is equal to, so we simply add this to 10, it becomes what? 10.0136 meter. Alright, so when that temperature is applied, the material was expanded to what? This length. L2 is equal to simply this. Alright, so before explaining or picking an example to explain the area expansivity and the volume expansivity, I want you to also keep this in mind, because it will also be an exam question, or it has been seen in your Jamb exam question over time. Now, the area expansivity is always given as 2 times the linear expansivity. The area expansivity is always given as 2 times the linear expansivity. Therefore, area expansivity, okay, which is denoted by beta, is always equal to 2 times the linear expansivity. The area expansivity is always given as 2 times the linear expansivity, whereas the volume expansivity V, which is always given as gamma, is equal to 3 times the linear expansivity. So this is also something you should also keep in mind. The area expansivity is always twice the linear expansivity, and the volume expansivity is always 3 times the linear expansivity. So if you're given a question which carries only the linear expansivity, but you're being asked to find the area expansivity or the volume expansivity, is as simple. You can always find the coefficient of area expansivity and the coefficient of volume expansivity using this relationship. Area expansivity is twice the linear expansivity, whereas volume expansivity is 3 times the linear expansivity. Now let's pick an example that explains this concept before we can now dive into the Jamb past question review, which we'll have for today in this video. All right. Now, let's consider this question on the board. The question says a cubic material of side 10 meter has linear expansivity of 2 times 10 to the power of minus 5 per degree Celsius. What is the superficial and volume expansivity of the material? Okay, so this is a very simple question. First of all, what is the superficial? Superficial simply means what? Area expansivity. Still the same thing as area expansivity. Now they're asking us to find the superficial expansion and the volume expansion of the body. But if you look through this question, you're given a cube. That's the first thing to make out in mind. You're given a cube of side 10 meters, and you're also given the linear expansivity, which is what? 2 by 10 to the power of minus 5 per degree Celsius. Now you're asked to find what? The volume expansivity and of course the area expansivity. It's as simple as this. Now, volume expansivity, I have said earlier that volume expansivity, okay, which is gamma, is what? 3 times the linear expansivity. And when we're given linear expansion of what? 2. Okay, so when linear expansivity, which is alpha, is given as 2 by 10 to the power of minus 5 per degree Celsius. So this simply means that the volume expansivity, gamma, is equal to 3 times 2 by 10 to the power of minus 5 per degree Celsius. And this is equal to what? 6 by 10 to the power of minus 5 per degree Celsius. So this becomes the volume expansivity. Also, to find the superficial expansivity, which is the area expansivity, areal expansion, okay, areal expansion, which is beta, is given as what? 2 times linear expansivity. So this is actually 2 times 2 by 10 to the power of minus 5 per degree Celsius. So this simply means that the areal expansivity beta is actually what? Is actually 4 by 10 to the power of minus 5 per degree Celsius. So that's how you find the volume expansivity or the area expansivity. All right, so keeping this in mind, let us start our Jamb past question review. All right, welcome back. So let's consider these two questions, which also tells us that this particular topic is a repeated topic in Jamb. So this is 2023 Jamb on physics, this same topic, thermal expansivity, and this is 2022 Jamb on physics, same topic, thermal expansivity. Let's start with the 2023 Jamb. Now the question says, this is question 23 in the 2023 Jamb. Question says, the linear expansivity of brass is 2 by 10 to the power of minus 5 per degree Celsius. If the sum of the volume of a piece of brass is 15 centimeter cube at 0 degrees Celsius, what is the volume at 100 degrees Celsius? So let's pick out the parameters. We are given the linear expansivity of brass. So linear expansivity, okay, which is alpha, is given as what? 2 by 10 to the power of minus 5 per degree Celsius. Now, if the sum of the volume of a piece of brass is 15 centimeter cube at 0 degrees Celsius, so this means that initial volume, okay, which is V1, is equal to 15 centimeter cube at 0 degrees Celsius. So which means initial temperature, which is theta 1, is given as what? 0 degrees Celsius. Question says, what is the volume at 100 degrees Celsius? Which means final temperature has been given. Final temperature, which is theta 2, is given as what? 100 degrees Celsius. Now we are being asked final volume. Okay, is the final volume we are being asked V2, which is unknown. Now these are all our parameters. Look at this question. You're given initial volume, initial temperature, final volume, and final temperature, but the coefficient of expansion there is what? A linear expansion and not a volume expansion. So again, it brings us to the idea I said earlier. Since these properties has to do with volume and not linear, it means we are going to be talking about the cubic expansion or volume expansivity. Now recall volume expansivity. Okay, volume expansivity, which is gamma, is given as what? Is given as volume, change in volume, which is V2 minus V1 all over the initial volume V1 times change in the temperature. You have this. Now the question is asking us to find the final volume, which is what? V2. So let's make V2 subject of the formula. Just like I explained earlier, this means now gamma all over 1. So it makes it easier for us to cross multiply. 1 multiplies everything at the numerator, gamma multiplies everything at denominator. So if gamma multiplies everything here, I have gamma times everything at denominator, which is now V1 times change in temperature. Okay, and this is equal to 1 multiplying everything at this numerator remains what? V2 minus V1, because 1 times anything remains that same thing. Now we are asked to find V2, so which means we need to send V1 over to this side of the equation. Negative V1 cross over and equal to sign becomes what? Positive. So I have gamma multiplying V1 multiplying change in temperature. If minus V1 crossover becomes what? Plus V1, and this is equal to V2. So this is what I'm looking for, V2. All right, we are given the initial volume. We can find the change in temperature, of course. We are change in temperature, change in theta, of course, is equal to what? Theta 2 minus theta 1. And theta 2 was given as 100 degrees Celsius. So we have 100 minus theta 1 was given as 0 degrees Celsius minus 0. So this still remains what? 100 degrees Celsius. So we have change in theta. Now, what is gamma? Remember, the volume expansivity, gamma is equal to what? 3 times linear expansivity. So this is equal to 3 times, what is the linear expansivity? 2 by 10 to the power of minus 5. So this is actually what? 6 by 10 to the power of minus 5 per degree Celsius. So this is now our volume expansivity. So if you put it into this equation, find gamma to the 6 by 10 to the power of minus 5. So we have 6 by 10 to the power of minus 5 multiply V1, which is the initial volume. The initial volume was given here as 15 centimeter cube. So multiply by 15, multiply by change in theta, which is change in temperature, and that gave us 100 degrees Celsius. So multiply by 100 plus V1, initial volume, which is 15, plus 15, and this is equal to V2. Now this implies that V2 is equal to, let's evaluate all of this now. 6 by 10 to the power of minus 5 multiplies 15, multiplies 100, simply gives us 0.09 plus, put down your 15 plus 15. So you see that the whole of this, once you add them all up, you have 15.09 centimeter cube for the final volume. And if you look through the option B gives us 15.09 centimeter cube. So option B is the correct answer. Okay, now it is important for you to know that when a question is given to you, you look at the answers to confirm what the unit. Since the unit is in centimeter cube, notice that we've not converted any of the units given to us. We also use 15 as 15 centimeter. We didn't change it to by converting or dividing to by 1000 or whatever. We didn't convert. We still left it as what? 15 centimeter cube and solved. Okay, so whenever the unit, but if the unit is not in centimeter, if it's in meter, then you have to now convert the volume to what? Meter, and solve it like that. But that's it for that particular question. Let's move now to the 2022 question. The 2022 question says, what is the relationship between the coefficient of linear expansivity alpha and the volume expansivity gamma? So it's simple. I already explained that earlier. Volume expansivity gamma is actually what? 3 times linear expansivity. So option C, 3 alpha, is actually what? The correct option. All right, guys. So that's it on linear expansion. I hope this video helps you as you prepare for your 2024 Jamb examination. Please, if you like this video, please do well to share your thoughts in the comment section. Share these videos to your friends who are also preparing for Jamb. And of course, if you're new to the channel, do well to subscribe to get or keep getting updates when the next video drops. As we promised, we are going to be covering physics, mathematics, and chemistry in preparation for your forthcoming examination. So do well to stay tuned while you get all those videos. Thanks and cheers.